Hi everyone, I'm Chao Wang, a PhD student from Huazhong University of Science and Technology. It's a great honor to present our work here. Our work addresses a crucial but often overlooked threat in mobile ecosystem, the Adware. Before diving into the details, let me start with some background information about why this research matters. Adware represents a unique challenge in mobile security. It is typically categorized as grayware or potentially unwanted applications, occupying a bigger space between benign software and overt malware, such as worms and trojans. According to Kapsky's recent report, Adware has emerged as a dominant threat in the mobile landscape in 2023. Despite Adware's significant threat, there's a considerable gap between its real-world impact and research attention. Current research has primarily focused on Adware identification method or debate on whether to classify Adware as malware. However, unlike general Android malware research, we lack in-depth understanding of Adware's fundamental characteristics. This gap largely stems from the absence of dedicated and well-noted Adware dataset. Okay, let me highlight our key contributions. First, we present Adware2, a comprehensive Adware dataset with family-specific payload analysis. It's also publicly available for the research community. And secondly, we real ecosystem insights. It includes systematic family naming patterns, diverse payload placement strangers, and Adware's prevention techniques. And our methodology consists of two main components. The first component focuses on dataset construction. We employed a comprehensive approach to collect Adware samples from multi-source. And the second component involves our novel payload detection method and addressed two key challenges. Our first step was systematic report collection. We identified 19 reliable source websites of renowned security companies and implement focused growing strategy to ensure we capture the relevant reports. We used carefully selected keywords related to Android Adware. Starting with 2,364 reports, we implemented a multi-stage filtering pipeline. Firstly, we narrowed down to reports mentioning Android in either their titles and contents, giving us 797 reports. And then through manual review, we identified 104 reports specifically discussing Adware. Next, we filtered for reports containing simple identifiers. Finally, we verified these samples through VerseTotal. This left us with 37 validated reports, and from which we collected 1,132 unique APK samples. Working with our industry partner gives us access to a massive collection of over 3 million APK fields from this extensive collection. We acquired 21,018 additional Adware samples. For processing these samples, we employed a systematic approach, used the AV class for family classification, and implemented controlled random sample with a maximum of 300 samples per family. For family labeling, we utilized AV class in conjunction with the VerseTotal reports, which provide us with comprehensive window analysis. We then applied strict filtering criteria to ensure dataset quality. Through this regional classification process, our final Adware2 dataset contains 15,996 unique APKs distributed across 118 distinct families. Okay, the approach to the Adware payload detection. First, let's clarify what we mean by payload. In the context of malware, a payload is the component responsible for executing malicious activities. This report can be located in Java, Kotlin package in index fields, and in resource folders, including ASEW fields and dynamically loaded decks or jar fields. Our detection method is based on a key assumption. If we separate and repackage the family's payload into a standalone app, it should still be recognized as belonging to the same family when scanned by VerseTotal. This assumption is not just theoretical, it's supported by previous research on harmful library detection. Our payload detection approach involves two key steps. Firstly, we use APK tool to unpack and compare each APK fields. Second, to handle obfuscated package names, we implement feature hashing. We compute hashes based on the API call frequencies with each package. This methodology ensures reliable payload identification even when developers attempt to hide their code through name identification. And for Java and Kotlin code components, we follow a three-step process. Firstly, we calculate feature hash for all secondary package with each family samples, and next we extract package corresponding to each unique feature hash. Finally, we repackage each extracted package into a clean APK template and verify it through virtual scanning. And for native library and dynamic load components, we use a different approach. First, we completely remove all DX content from the APK, and then we extract all resource fields. This includes ISO fields, jar fields, and additional DX fields. Finally, similar to the approach for Java code, we repackage each component individually and verify through VS-Total. The evaluation focuses on two key research questions. Research question one addressing the validity of our code assumption, and the research question two examines the effectiveness of our payload detection approach. To verify the key assumption, we start with a focused validation using well-documented samples. We selected 36 samples across 8 families from 10 reports with detailed payload information. 29 out of 36 samples showed perfect family name matches. The remaining 7 samples revealed interesting license variations. Take the ghost team for instance. It was identified as a ghost team, where team is abbreviated to TM, where maintaining the same pronunciation. Based on these findings, we conduct a comprehensive analysis. We manually mapped allies across all 118 families in our dataset. Our findings on payload distribution based on our random sampling of 30 families from our dataset. First, all 30 families contain DEX payloads, which broke down into 3 categories. 17 families showed unique and consistent package names, until family used multiple package names but maintained similar code structures. And my family Kuga employed package filters but was still identifiable through its component Kuga structure signature. Beyond the DEX payloads, 8 of these 30 families also contained additional result payloads. Okay, let's see the results part. The table 1 presents a comprehensive overview of the top 20 Android Adware families from our dataset. The table calculates key metrics including the number of samples and the average Adware tag count for each family. Additionally, the table provides insights to family naming patterns and crucial information on payload location. The 118 Adware families with our dataset are each characterized by 2 key metrics: the sample quantities and the average number of Adware tags. The figure box 1 presents a box plot illustrating the distribution of sample quantities across Adware families, and the figure 2 presents the distribution of average Adware tag number across families. And our findings on Adware families name patterns, which revealed 2 distinct categories. Firstly, families named after advertising networks were identified at least 37 families following this pattern. And second, families named based on their behavior characteristics. These families typically show more complexity. Each contains multiple variants. To Adware family payload location, our analysis successfully identified the payload location of 111 out of 118 Adware families with our dataset. The distribution of payload location as shown in this figure. Regarding payload location with DEX fields, where we observe 3 distinct patterns. First, regarding package name obfuscation. 31 families employ the same payload but with different package names. Second, we found significant version diversity. For 47 families contained multi-versions of the same payload package. Third, we discovered a stringent payload placement. 17 families had their payloads with common package names. This represents a sophisticated approach to be aligned in with legitimate code. Our findings about payloads located in resource folders, we discovered that 36 families carried payloads with apps resource folder, distributed across these three main categories: the native libraries, the dynamic loadings, and manifest detection. Okay, let me conclude by discussing our study's limitations and future directions. First, regarding to data site comprehension is despite our extensive collection of efforts, we acknowledge that we may not have captured all existing Adware families given the vast scale of the Android ecosystem. And second, we faced several technical detection barriers. Advanced obfuscation techniques, particularly package flanting, and sophisticated app packing method that had a code structure. Finally, it's dynamically loaded payloads not present in static analysis. However, it's important to note that their limitations only affect 7 out of our 118 families. And the third, we encountered temporal challenges. Many historical samples remote servers were no longer active, which limited our ability to perform dynamic verification. Looking forward, we have identified three key directions for future research. Firstly, we plan to study how Adware manipulates the AD deliver timing, placement, and user interactions. Second, we want to examine technicals used for click fraud, view manipulation, and fraudulent review generation. Finally, we want to exercise how Adware collects, retracts, and potentially leaks user private information. Has come to the end. Let me conclude by highlighting our key contribution and their implications. First, data creation, we have established Adware Zoo, the first comprehensive Adware dataset containing 15,996 samples across 118 families. Second, ecosystem understanding, our analysis have revealed systematic patterns in how Adware families are named, while also uncovering diverse payload strings and sophisticated emission techniques. And the third, real-world impact, our findings highlight the urgent need for enhanced mobile advertising regulation and more effective detection strategies to support future research in this critical area, while making our dataset publicly available at the site. Okay, thanks for listening. I'm happy to have any questions. Thanks.